All right, can you still see the screen?
Yeah.
Awesome. So a couple new things for this week. I'm going to walk through them really quick, and then if you've got questions, I'll open it up. So from pre-calculus, all of our old rules still apply. So in order to be continuous, we have to have a general limit. So that means as we get really close to some value from the left and from the right, we have to be approaching the same y value. In order to be continuous, when I actually plug in the point, I have to be at the same y value. If we are removable, then I'll have a general limit, but when I plug in the point, I don't end up there. So I'll either have a white space like this where my point doesn't exist, or I'll have a black dot somewhere else that says my point exists somewhere else, even though the limit is going to the same y value. We also have one more major category of non-removable discontinuities in pre-calculus. That's still true in AP calculus, but we can be a little bit more specific. In pre-calculus, a non-removable discontinuity was any time that one of our one-sided limits did not match the other, or any one-sided limit approached infinity. For AP calculus, we can break this down into three subcategories. So an infinite discontinuity is when one of our one-sided limits approaches plus or minus infinity, like this. So here, as we get really close to x equals -1, from the left, I'm approaching negative infinity. From the right, I'm approaching positive infinity. For a jump discontinuity, this would be whenever any of the one-sided limits are approaching different values. So both one-sided limits exist, but are different. So in this case, from the left, I'm approaching a y value of 4, but from the right, I'm approaching a y value of 2. And lastly, an essential discontinuity is anytime that one of our one-sided limits does not exist. It could also be what happens if both of our one-sided limits don't exist. So that would be just a point floating in free space. Or if we had an oscillating function. So that would be something like the sine of 1 over x, as you approach 0, oscillates forever. Okay, I'm going to go ahead and graph that just so we can see what happened. So this is the graph of the sine of 1 over x. So the graph of sine of 1 over x, if I plug in a number that's really close to 0, I'll be dividing by a super small number. And when I divide by a small number, I get bigger. So this fraction on the inside of my sine function is going to go to infinity. And the sine of infinity bounces between 1 and -1. So if I zoom into our graph here, you can see that no matter how far we zoom in, we're going to keep bouncing forever. Oh, I've zoomed in as much as I can apparently, but doesn't matter how far we zoom in, it's just going to keep bouncing. Any questions on our categories here for continuity?
No.
Okay, then one more thing to add. In order to test and see whether we are differentiable, we have to be first continuous. And in order to be continuous, we must have a general limit, which is equal to what happens when I plug in the point. But we also must have our derivative approach the same value from the left and the right. Here's what I mean by that. Here I have a cusp. So at this point at x equals 3, I am still continuous because my limit from the left and the right are the same. And when I plug in the y value, I get the same thing. But my slope is not the same from the left and the right because I had a positive slope on the left side, but a negative slope on the right side without actually hitting 0. So I could say that this point is continuous, but not differentiable. Not differentiable because this second condition down here is not true. So a flow chart. All functions that are continuous must first have a general limit. All functions that are differentiable must first be continuous. But not all continuous functions are differentiable, and not all functions with a general limit are continuous. Any questions so far?
No.
Okay. Then let's do some practice. Jump from here, I think. Okay, so at x equals 1, what is my limit from the left?
-1.
Okay, what's my limit from the right?
Still -1.
General?
-1.
And if I plug it in?
-1.
So what's my continuity?
C, right?
Yep, continuous. Okay, at x equals 2?
From the left side is 1. 1. 1. 2.
Sorry, what should this be?
Sorry, 0.
0. And what is this?
Removable.
Removable, perfect. Okay, at x equals 3?
-4. -2. Does not exist. -2. Non-removable.
Okay, you're right, but can you be more specific with our new categories?
Okay, wait. Is it jump discontinuity?
It is. So this is a jump discontinuity. Jump because our two-sided or our one-sided limits exist but are not the same.
Mm-hmm.
Okay, x equals 4.
X equals 4. Positive infinity. Positive and positive does not exist. It's non-removable.
Okay, and
And infinite.
infinite. Perfect. Okay, I think you got this, but I'm gonna keep going and finish this off through x equals 10. So as fast as you can.
5, -4, -4, -4 does not exist, and removable.
Awesome.
-3 does not exist, and -3 non-removable. And it's essential because there's only one.
Perfect. At least one of the one-sided limits does not exist. So this is essential. Okay.
7, -2. Oh wait, sorry, does not exist. -2 does not exist. Non-removable, and it's still essential. Oh yeah, essential.
Awesome.
Number 8 is -2, -2, -2, and -2. C.
Continuous. Perfect.
-1, -2 does not exist. -4, and that's non-removable with jump.
Awesome. And last one.
Positive, infinite, negative, infinity, and does not exist. does not exist. That would be not removable and infinite.
Infinite, perfect. Okay. So if I was going to look at not the graph, but functions instead, as long as your denominator equals 0, then we can say that you are not continuous because we have a point where we are undefined. If your denominator is 0, and we can cancel. So like this one on the left, if I factor an x out right now, I've got x times x minus 3 over x minus 3. And my x minus 3's right now can cancel. Then we can say that this is a removable discontinuity because we were able to cancel that discontinuity. So for this one, there's a removable discontinuity at x equals 3. For this one on the right, x minus 7 does cause us to divide by 0, but there's nothing to cancel this time. So because there's nothing to cancel, this is not a removable discontinuity, and this will instead be an infinite discontinuity. Anytime the denominator is 0 and does not cancel, we'll end up with a non-removable infinite discontinuity. Anytime that the denominator is 0 and we can cancel, we will end up with a removable discontinuity. Infinite discontinuities are also known as vertical asymptotes and are usually subscripted VA. So I have a vertical asymptote at x equals 7. Any questions on vocab stuff?
What's VA again?
VA stands for vertical asymptotes.
Oh, okay, I see, yeah.
On our graph, those vertical asymptotes are those dashed lines that our function never crosses.
Yeah.
Okay. So the way that College Board likes to ask these questions in the AP exam is to give some sort of a piecewise function and ask you about the continuity and differentiability of them. So here's an example from a previous AP exam. I don't know if I actually pulled this from a previous test or if I just wrote one that's in the same style, but it looks like this. So I'll work through the first one with you, and then if you can do the next two on your own, and I'll just kind of guide you if that's okay. So I'm looking at x equals 3. I want to know whether this function is continuous, differentiable, neither or both. So first, in order to prove that we are continuous, I have to have a general limit first, which means the limit as x approaches 3 in our case from the left must be equal to the limit as x approaches 3 from the right. And all of that must equal f of 3. Okay, if I take the limit as x approaches 3 from the left, would I need to use the top function or the bottom function?
Bottom function.
So if I'm approaching 3 from the left, I'll be less than 3. So this will be 2.9 repeating. So I'll end up plugging into the top. So I'm going to plug 3 into the top equation. What happens if I plug in 3 to the top equation?
We plug the 3 in.
Yes.
Okay. So it will be 11.
11, perfect. And then I'm going to take the limit as we approach 3 from the right, which means we're greater than 3. So I'll use the bottom equation. What happens if you plug 3 into this bottom equation?
11.
Also 11. If we are equal to 3 exactly, do I need to use the top function or the bottom function?
The bottom function.
Bottom function, which is 11 again, because we already calculated it for being greater than 3. So everything is 11, and I can say that the function is continuous at x equals 3. Okay, that doesn't tell us the answer. That does tell us it's not D. But the rest of these are okay for A or C because we could be continuous and differentiable. So I'm going to test one more thing. To be differentiable, we must be continuous which means our general limit as x approaches c of f of x equals f of c.
Mm-hmm.
And the limit as x approaches c from the left of the derivative must be equal to the limit as x approaches c from the right of the derivative. That's very similar to what we did last time, except instead of plugging into the original function, I'm going to have to derive. So I'm going to go ahead and put a break here, and we'll go ahead and derive our function. I'll change colors for this. So in green, I'm going to write a new piecewise function for the derivative of f. What's the derivative of the top function?
2x.
2x, and I'm going to use that whenever x is less than 3. What's the derivative of the bottom function?
6.
6. Oh, let's afraid of that. Just lost my pen again. Do I still have a mouse? Okay, I have a mouse, but don't have a cursor.
Mm-hmm.
Okay, we'll try that. So this will be uh, 6. Six whenever x is greater than or equal to 3. All right. So with that, I need to test and see does the derivative from the left equal the derivative from the right? So if I'm approaching this from the left, I can use the top equation. So for the top equation, if I plug in 3, what do I get?
6.
I get 6. What about from the bottom equation?
Oh, wait. Oh, it's the same. Okay, 6.
It is the same. Okay. So I can say as f prime f prime's limit as x approaches 3 from the left equals the limit as x approaches 3 from the right. Because they're both 3, we are differentiable. Okay, any questions on this one?
No.
Cool. Try the next one. What do I have to do first?
Fx equals to, wait, the limit thing, right?
Okay, so we're going to test the left and right side limits.
So limit x to pi to negative. Is that, yeah. And then fx equal to limit x up to the pi positive. And then equal to x equals to pi.
Perfect, or f at pi. So if I plug in pi into our top equation here, I'll get the sign at pi over 2. Do you remember from the unit circle what is the sign at pi over 2?
No. Oh,
Okay,
wait,
so
oh. 1.
perfect.
Yeah.
So the sine at pi over 2 is 1. So my limit from the left is 1. And then what is, if I plug in pi, this will be the cosine at pi.
Okay. There will be -0.
So this will be, I've got the negative on the outside here that's going to stay. But the cosine at pi is my x value. So that's going to be -1 at that point. So I'm going to have -1, which is +1. And then if I plug in pi, we're also using the same equation. So that's still going to be the same thing.
Okay.
So I can say that these functions are what?
Continuous.
They are continuous. Perfect. What else do I need to do to prove their differentiability?
We have to derive them.
Okay, we have to derive them. I'm going to change colors again. So this is f prime of x is equal to our new piecewise function. What happens if I derive the sine of x over 2?
Um, 1/2. Oh, okay, yeah. Cosine.
Okay, awesome. So this top part's going to be 1/2 cosine x over 2. Normally I would write my bounds here, but I'm writing with the finger now, so everything's a little bit fatter than usual. So I'm kind of out of space. This is, you write 1/2 cosine x over 2, and that's still going to go from -infinity to pi. And then what about the bottom part?
Positive sign.
Perfect. Positive sine of x. And that's going to happen for all values where x is greater than or equal to pi. All right, so I just need to test and see if these are the same for the derivatives. So if I plug in pi into 1/2 cosine pi over 2, what is the cosine at pi over 2?
0.
0, perfect. So for a test for differentiability,
0.
the limit as x approaches pi from the left of f prime x is 0. And the limit as x approaches pi from the right of f prime x is what? What's the sign at pi?
Sine of pi.
Mhm.
Oh, it's also 0.
Also
Wait.
0.
Yeah.
Okay, what does that tell us?
No, it's also differentiable.
Perfect. This one is both continuous and differentiable.
Okay.
Last one.
Okay, same thing. Limit x to the pi positive.
Okay, this is my bad, I think, on the slide. I'm going to go ahead and do the 4 instead.
Okay.
Sorry.
4 positive.
Okay, so we'll do from the right first.
Oh, okay.
It's okay, you can choose the order. So we'll need to do both eventually.
Okay. And then 4x equals 4.
Okay, so you said you wanted to do the right side first. So if I plug in value 4 from the right, what's going to happen?
It will be the bottom one. So it will be 3.
Perfect. And if we do 4 from the left?
It will be 2. And so it's
2.
not continuous.
Right. It's not continuous, and because we must be continuous in order to be differentiable, it's not differentiable either.
So it's never B.
Uh, yes, B is not possible.
Okay. Wow.
Okay, this is more in the pre-calculus section of the homework, even functions versus odd functions. Even functions are whenever you plug in the negative version of your input, you get the same version, you get the same answer as if you plug in the positive version of your input. So that means your reciprocal about you're reflected about the y-axis. So if I had a piece of paper and you folded it about the y-axis, you would end up being symmetric. Examples, I've got x squared here. If I had this piece of paper for x squared and I folded it in half, I would end up having the lines match. Odd functions are, if you plug in the negative input, you end up with -1 times your original input. So that would be something like this in your graph. I'm symmetric about the origin for these, for odd functions. If you were to take two people sitting at different sides of a table looking at the graph, so here I've got Eric and Andrew that are both looking at their sheet of paper. What Eric sees from his perspective is exactly the same as what Andrew sees from his perspective. If we were to rotate this paper 180 degrees, the graph would still look like the same shape. Mathematically, though, formulas would look like this. Any questions on even versus odd functions?
Will it tell us if it's even or odd?
Depends on the question. So I believe for the questions that we had for the homework, they just asked you whether this was an even function or an odd function for your final answer. And it was either x squared or x cubed. I don't remember, but
Okay.
okay. Then lastly, I've got a couple theorems. Extreme value theorem says as long as our function is continuous, we must have at least one maximum and one minimum. Even if we had a function that was just a straight line, so something like this. In this case, all of my points are maximums and all of my points are minimums. So there is at least one maximum and at least one minimum on that function. This also works for any interval, so any section of a function from point A to point B. As long as we are continuous for all of our points, there will be at least one maximum and at least one minimum. Okay, so here's an example. Our function is defined for some interval a to b, and my y value at a is the same as my y value at c, is the same as my y value at b. I'm going to draw out what that means. Okay, we were told that c is inside the interval a and b. So right now c is some x value between x equals a and x equals b. So our function looks something like this. I'm going to draw a couple options that would still work if we are continuous. So I could do this. I could do this. I could curve, so do something like this. All of these are possible because it was continuous on the interval from A to B. So first, which of the following must be true? The first one says we do not have a minimum or a maximum on our interval. Is that true or false?
False.
False. Okay. Why is that false?
Because it's told us that f is continuous on A and B. So it must have a minimum and a maximum.
Perfect. So which one of these is true?
Is it?
Sorry, say again?
D.
Okay, I haven't had a hard time figuring out which letter you said over the mic. So alpha, alpha, Bravo, Charlie, or Delta?
Delta.
Delta. Okay, cool. Awesome. So this one's true because of our extreme value theorem. So the way that College Board prefers to ask these nowadays is actually as part of a free response question. So they might ask you to prove that there is a minimum or a maximum on this interval. So you would have to prove that the function is continuous, like we did previously for that piecewise function. And then once you prove that the function is continuous by checking the limits from both sides and what happens when you plug in the point, then you can go back and say, because of the extreme value theorem, we must have a maximum and a minimum on that interval. Intermediate value theorem. And the intermediate value theorem says if we have an interval A and B and we are continuous on our interval again, then we must pass through all y values between f of A and f of B. So as long as we started here, and I'll say y equals 4, and we end here at y equals 2. As long as our function is continuous, we have to pass through every y value between 2 and 4 at least once. It is possible to pass through them twice. So we could have something like this, where I pass through all of these values a bunch of times. But I have to pass through each value at least once in order to get from point A to point B. Okay, here's a couple of multiple choice examples of what that would look like. So from the BC exam, we are continuous from -3 to 6. F of -3 is -1, and f of 6 is 3. I'm going to draw out what that looks like. F of -3 is -1. And f of 6 is 3. Okay, so something like this. I want to know which of these must be true. So Nani for the first one. Does our y value at 0 have to be 0?
Maybe though.
Maybe. So it's possible that that's true, but it does not have to be true. It's possible for me to draw this line like this and not pass through that particular point. So this one does not have to be true. Okay, what about B?
It didn't give us the number of 4/9 though.
It did not. This is also talking about f primes. This is the slope. Sorry, go ahead.
It will be the same as A.
Yes, so that this does not necessarily have to be true by the intermediate value theorem. I will show you one more theorem that will tell us about the slope, but the intermediate value theorem doesn't talk about slope. so this one's not true. What about C?
Maybe.
Maybe. It does not necessarily have to be true because it's possible for us to go above 3 or
Yeah.
below -1 and still connect the dots.
Yeah.
Okay, excellent. What about D?
The well, can you draw FC equals to 1?
FC equals 1, so C is some value, they're saying, between -3 and -6. So I'm going to draw C here. F of C is +1. But C could be any number between -3 and 6.
Yeah.
Okay,
I'm not sure.
This one is true. The intermediate value theorem says we have to pass through every y value between our y value at the first point and our y value at the second point at least once. So there will be at least one C between -3 and 6 where we hit y equals 1. Okay, the reason why E is not true is because our interval has changed.
Oh, I didn't
So
realize.
C for this one is only going from x is -1 to x is 3, which would be from here to about here. And that's too limiting. We know that we have to pass through 1 at least once between -3 and 6, but we could do that before -1 or after 3, and that would still be okay. So something like this.
Okay.
Right, and for number 2, our function is differentiable this time on the open interval from x equals 1 to x equals 10. F of 2 is -5, f of 5 is 5, and f of 9 is -5. I want to know which of the following must be true. Okay, I'm going to draw out what we were given so far. When x is 2, 5, and 9, we have y values. So I'm not going to draw this to scale, but when x is 2, 5, and 9, we have y values of -5, 5, and -5. Okay, so something like this is everything we know so far. Okay, so the first one says f has at least 2 zeros. A 0 is any time when we touch the x-axis. Does that have to be true or false?
It can be true.
Okay, this one must be true. We have to have at least 2 zeros in order to touch all of these points. That's actually the intermediate value theorem twice. And the intermediate value theorem guarantees I'll touch 0 at least once between these 2 points, but also at least once between these 2 points.
Okay.
Okay, so this one is true. The graph of f has at least one horizontal tangent. Horizontal tangent is a point where our slope is equal to 0.
How do we know that?
So we know that actually because we were told that this is differentiable. If this had just been continuous, then this would not necessarily be true because it would be possible to draw a function like this.
Oh,
So with a sharp point, but because we're differentiable, and that means the limit from the left of our slope has to be the same as the limit from the right of our slope for every point, which means we have to have a smooth transition where our slope is always the same from the left and the right.
so it's true also.
So this one's also true. Okay, and for the last one, for some value between x equals 2 and 5, the y value must be equal to 3.
Um, but we already have 5 though.
We do know what 5 is, yes. Erase our mark line here. So between this point and this point, between x equals 2 and x equals 5, does the y value at some point c between them? So I'll call c some point between x equals 2 and x equals 5, have to reach a y value of 3.
Maybe.
So this one is definitely true.
Okay.
Because of the intermediate value theorem, if I know that the y value is -5 when x is 2, and the y value is 5 when x is 5, then I have to pass through every y value between -5 and 5 at least once.
So 3 is invalid.
Right, I have to pass through 3 at least once between them. So for some value c, we don't know which value, but for some c between 2 and 5, this will be true. Okay, so this one is all 3. Any questions on either of these two?
No.
All right, last theorem for today. The mean value theorem says as long as we are differentiable this time, this is the only theorem that requires us to be differentiable. The other two were only continuous. As long as we are differentiable, then there will be some c between point A and B, such that the derivatives, that's your instantaneous slope at c, or this tangent line, is equal to the average slope between A and B. I can write that like this. Our derivative would equal our average slope. As long as we are differentiable on A and B, this will be true for at least one point C. Now, it is possible for this to be true for more than one point C. So here's my secant line between A and B. And then here's my function in red. I'm going to have two C's, so C1 and C2, where the line tangent to our function is parallel, which means it has the same slope to our secant line here in blue. But the mean value theorem guarantees that there will be at least one point.
Okay. So there's two slopes.
In this case, there's 2 points where the slope is the same as my average slope. In these examples on the right, there's only 1 point where the slope is the same as the average slope. But the mean value guarantees there will be at least one. There could be 2, 3, 4, infinity, but there must be one. Here's what the math is going to look like on your AP exam. And then I'll break after this and show you how a couple of ways it can be used in the real world. So for this one, I want to find values of C. So that's values between the 2 points in our interval that would satisfy the mean value theorem. So I'm looking for points where the derivative is the same as the average slope. So my average slope is y2 minus y1 over x2 minus x1. We're in function notation, f of b minus f of a over b minus a. So first I'm going to get our y values by plugging in x equals 2 and x equals 5 into our equation to get our y values. Are you okay on our first step?
There's no point of 2 and 5 here though.
So what we're doing, laser pointer actually. So what we're doing is I'm taking this equation here and I'm plugging in x equals 2 into this equation. So that's what this part in blue is. If I plug in x equals 2, I'll get 2 squared over 2 minus 2 times 2 minus 3. So that's just replacing x in this formula with x equals 2. If I do, this will be 4 over 2. So that's 2 minus 4 minus 3. 2 minus 4 minus 3 is negative 5. Do the same thing down here by plugging in 5 into our equation. So if x is equal to 5 up here, then this would be 5 squared over 2 minus 2 times 5 minus 3. 5 squared over 2 minus 2 times 5 minus 3 is 25 over 2 minus 20 over 2 minus 6 over 2. Or 25 minus 20 is 5, minus 6 is negative 1. So this is negative 1 over 2. Are you okay in the first step?
Yes.
Okay, so then I'm going to go to my average slope. This is f of b minus f of a. So that's f of my second one. So that's f of 5 minus f of 2. F of 5 is negative 1/2. So that's negative 1/2 minus negative 5 over our x values, b minus a. So that's 5 minus 2. Should give me my average slope. So I can say our average slope then. Our average slope then is negative 1/2 plus 5, which is 10 over 2. So that's negative 1/2 plus 10 over 2 is 9 over 2. And 5 minus 2 is 3. If I multiply this out, this is the same thing as 1/3 times 9 over 2 is 9 over 6, which if I simplify is 3 over 2. So my average slope between x equals 2 and x equals 5 is 3 over 2. Are you okay so far?
Yes.
Okay, I'm going to draw out what we just did really quick. Or attempt to. Okay, I've got x equals 2, and we were at negative 5. Or here-ish. Then we also had x equals 5, and we were at negative 1/2. And if I was to draw a line between those, that line would represent our average slope. And our slope of that line was 3 over 2.
So the 2 and the 5 are both, the FA and the FB are always the x-axis, right? The x. There's no y here.
So our x values are a and b. Our y values are what happens when we plug it in. So our y value would be f of b or f of a.
I see, okay. But the 2 and 5 are the x values.
Yes. Okay, so according to the mean value theorem, this average slope should be equal to our derivative. I'm going to go back. Here's our formula. Our derivative has to be equal to our average slope, fb minus fa over b minus a. So we've got this part already. This part was 3 over 2. So I'm going to set 3 over 2 equal to the derivative of my original function. If I derive this, I'll get 2 times x over 2 to the first power, which is x minus 2 minus 0, or x minus 2. So if I solve for x, because 2 is 4 over 2, I can add it to the other side, and I'll get 3 over 2 plus 4 over 2 is 7 over 2. So x equals 7 over 2, which is 3.5, or right here. My slope of this line will be equal to my average slope. Can I carry this over into a different program so I can use a ruler really quick? And we'll show that. Okay, so we had points here that looked like this. At x equals 2, we were here at 5. At x equals 5, we were here at negative 1/2 for our y values. So using a ruler, lost the ability to change this apparently. Okay, I guess I can't use a ruler. I've got a line between these two. That will look like this. Okay, we've got a line between our 2 points that looks like this. And then at x equals, we said 7 over 2. Which is 3.5, or here, is a point where the derivatives, that's the slope at that one point, should be the same as our average slope here in red. So if I draw that out, maybe in green, I'm going to draw a line that only touches our curve at that point. That line would look like this. Ooh. Okay, something like that. We end up with the exact same slope of both lines. Do you understand what's going on?
Yeah.
Okay. Let's see, the rest of these are limits questions that they had last time for L Hospital's role. I guess I'll go through that really quick since we're here. L Hospital's rule says if you end up getting this particular form, 0 over 0, or plus or minus infinity over infinity, so we call these indeterminate forms, then our limit will be the same as what happens if we take the limit to the same value of the derivative of the top divided by the derivative of the bottom. And we can use that as a shortcut to solve a bunch of limit problems. So for example, for this one over here, if I plug in 0 right now, I'll get 2 times 0 over the natural log of 1, which is also 0. So I could say that this equals 0 over 0. With L Hospital's rule, for number 1, what happens if I derive the top and the bottom?
Um, I'm not sure.
So we're going to derive the top and the bottom separately. So if I derive 2x, what do I get?
2
And if I derive the natural log of x plus 1?
x plus 1 over x plus 1.
1 over x plus 1. Okay, there would be chain rule there, but chain rule would just be multiplying by the derivative of x, which is 1, so I don't need to write it. If I plug in x equals 0 right now, what happens?
2 over 0.
Oh, not 2 over 0.
Infinity.
Not infinity either. If x is 0, this will be 1 over 0 plus 1.
It will be 1.
Right.
So the answer. Okay.
Yes. Okay, same idea for number 2. If I plug in 0 right now, I'll get e to the 0 power minus 1 over 0. Anything raised to the 0 power is 1, so this is really 0 over 0. So we can use L'Hospital's rule and derive the top and bottom separately and try again. What happens if I derive the top?
5x.
So this would be 5
Yeah.
e to the 5x, right? And on bottom?
3.
3. If I plug in 0 right now, what happens?
The top one will be 0. Oh wait, sorry. There's yeah.
Okay, the top one will become, this will be 5e raised to the 0 power over 3.
5 times 1, right?
Right.
So the answer is D.
Awesome. Okay, and that's everything we covered with the other class, I think. Did you have any other questions on the homework?
Yeah.
Okay, let me pull it up really quick. Um, okay, I believe this is the BC one. So we've got pre-calculus and limits. Which questions did you want to talk about?
Last question. Like last 3 pages.
Last 3 pages. Okay, definition of a derivative. Are these ones you mean or not?
Yeah. Yeah.
Okay, so let me talk concept first. So way back at the very beginning of pre-calculus, we defined our derivative like this. So if, oh, there we go. If we had a function that looks like this with 2 points. So I'm going to call these points point. I was going to do point A and B, but I'm going to call this x and x plus a little bit, I think. Is how we did it last time. So this is x and f of x. And this is x plus some change in x. And f of x plus some change in x. Then that means we have a space between these 2 points of change in x, right?
Mm-hmm.
Okay, so if I was to take the limit as that change in x approached 0, of the slope between these 2 points, or y2, f of x plus change in x minus y1, f of x over x2 minus x1, which would be x plus change in x minus x, which means the x's would cancel and I'd be left with change in x. Then I would end up with the slope at a single point instead of the slope between 2 points, because if there's no distance between the 2 points, then I'm getting the slope at 1 point. This is our definition of a derivative. Okay, any questions on this part?
No.
All right, so that's really what we need for these questions. So for this first one, we're looking for which of these answers could be equal to our derivative at the point E. Uh-oh. Nope, okay, here we go. Which of these is equal to the derivative at E? So with our definition of derivative then, if instead of writing delta x approaches 0, I use this new variable h instead, then our definition of a derivative would look like this. F prime at E is equal to our function. Oops, I need a limit here first. The limit as h approaches 0. So I'm going to copy the exact same definition of a derivative, just use h instead of dx, of our function at our x value, which is e, plus our change in x, which is h, minus our function at e over our change in x, which is h. So my function is e to the x, so plugging that in, this would be e to my input, which is e plus h, minus our function at e to my input of e, over h. If I take the limit as h approaches 0, should be equal to the derivative of our original function at e. Which of these matches?
E.
Yes, e matches. Are you okay on the first one?
Wait. Oh. Okay. Yeah.
All right. That was trickier than I thought, actually. So just replace that e with x.
Oh.
We've got to be really
Actually,
careful, but this one is e, you're right. I just didn't realize these were as similar
yeah.
as they are. This one's missing an e here. This should be e instead of 1. This one's got an x instead of plugging in the e. Well, okay, so this one is e. Same idea here, actually.
Can I try?
Yeah.
Okay, so but the x plus h is already given, no.
Yes, this one's kind of working backwards. This is my definition of a derivative. So if you can figure out what the original function is, then we can just derive that to get our answer. What do you think the original function was?
Oh, maybe between B and C.
I'm going to zoom out. This is my definition of a derivative. F of
Yeah.
x would be my original function.
Oh. Okay.
Okay, so coming back in here, what's our original function?
C. Wait, it will be negative tangent 3x.
Is this one would be the tangent of 3x? Since our formula has the negative inside it.
Yeah.
What happens when I derive the tangent of 3x?
It becomes secant. Oh, B.
B, right? 3 secant squared 3x because of chain rule.
Wow.
What about this one for 10?
Okay. D.
Right.
Okay. Oh, okay.
And this one for 6?
So, mm, there's no. It'll be 0. No, it'll be D. Wait, D.
So our original function is 8
A.
times x to the 8th power, right?
Mm,
If I derive that, what's going to happen?
but there's no X though.
Our x is 1/2, but I'm going to derive, then we'll go back and plug in that point.
Oh.
So what is
That 64x. So the answer is
what's the power?
the power is 7.
Okay, and then if I plug in 1/2 right now, then y prime at 1/2 would be equal to 64 times 1/2 to the 7th power.
Oh, the answer is B.
Right.
Mhm.
Oh, wait, hold on. 1/2 to the 7th. Yeah. B, sorry.
Mhm. Mhm.
That is 64. I'm just going to write 2 to the 6 times 1 over 2 to the 7th then. Gives me 1/2. Okay. I think you're okay on this section now. Were there any of the ones that were on the earlier limit section that you needed help with?
Well, the limits. It only has a page. I'm not sure for 3, 42, and 18. Yeah.
3, 42, and 18. Okay, so this one first. We are told that our function is continuous at x equals 2.
Okay.
If our function is continuous at x equals 2, then
Yeah.
that means our general limit has to be the same as what happens when we plug in the point. So these two pieces of our function have to be equal to each other.
Yeah.
So I can use that to solve for k. I'm going to do this, I think, and transfer this over again. This might be easier without the pen working. Okay, so as long as we are continuous, my general limit as we approach this has to be the same as what happens when we plug in the point. Our general limit would use the top function. So in order for this to be true, the square roots of 2x plus 5, Minus the square root of x plus 7 over x minus 2 must be equal to k. Are you okay with the first step?
Yeah.
All right. So I need you to solve for k. When x is 2, what do I have to do?
Plug x in, right?
Right. So I'm going to replace all of these x's with 2's. When I do, what's going to happen on top?
Will become negative.
Okay, this is 4 plus 5 underneath the root. What's square root of 4 plus 5?
3. 3 minus minus 3.
I've
Wait,
got,
yeah,
you're right. So 3 minus 3,
0.
yep, over 2 minus 2.
So
So I've got 0 over 0.
1.
0 over 0 is not 1 necessarily,
Oh, okay.
but we could use L'Hospital's rule to try and figure out what's going to happen here, maybe. So what number am I approaching? This is undefined, which is not a set value. So what I'm really doing is this. It's equal to, give more information here. K is equal to the limit. Oh, I'll replace it. Limit as x approaches 2 of our original function here. If we just plug in 2, we get 0 over 0. So I'm going to have to try again in order to figure out what this limit is using L'Hospital's rule. If we use L'Hospital's rule, what happens when you derive the top?
Square root of 2.
What happens if you derive the square root of 2x plus 5? If you hint, square root of 2x plus 5 is the same thing as 2x plus 5 raised to the 1/2 power.
Yeah. Over x, right?
So we're over x minus 2. I want to derive the top and bottom separately for a hospital's rule.
It'll be 1/2 times 2 minus 1/2 minus 1/2 over 1.
Okay, I'll throw that in again. So this was, you said 1/2 times, this was 2x plus 5 raised to what power?
Um, um, Negative 1/2
Negative 1/2, perfect. And chain rule times.
times 2.
Okay, minus the other term.
Minus 1/2 times x plus 7 times 1.
X plus 7 raised to what power?
Oh, negative 1/2.
Okay, times 1, you're right. And that's all divided by 1, which you told me earlier. So I'm going to simplify, and we'll be ready to plug in. So this is the 2 and the 1/2 will cancel. So that leaves me with 1 over square root 2x plus 5. Minus, I've got 1 times the 1/2, 1 over 2 times the square root of x plus 7. Okay, and then I still need to take our limits as x approaches 2. So we're going to plug 2 back into this. What's going to happen if I plug in 2 right now?
Um, 1 over 3 minus 1 over 3. Oh no. 1 over 6.
Okay, 1 over 3 minus 1 over 6.
Sorry,
I'll need to get. Sorry, go for it.
That's 1 over 2. Wait. Yeah, that's 1 over 2.
This should be. This should not be 1 over 3. This should be. This should be 1 over 3, not 1 over 2, I think. That's if I plugged in 2, this is square root of 9 is 3. This is square root of 9 is also 3 times 2 is 6. So we got 1/3 minus 1/6. What is, if I want to get a common denominator, what are my common denominators then?
Mm, 2. 2 over, wait.
1/3 is how much over 6?
2.
Okay, 1/3 is 2 over 6. 1 over 6 already has our common denominator, so 2/6 minus 1/6 is
1 over 6.
1/6. Okay, so this is what k should be equal to then. Okay, so that's 1/6. You had a couple more. You said these two, right? Okay, so for this one, if I just plug in 0 right now, the cosecant at 0 is 1 over the sine at 0, would be undefined.
Yeah. So it will only be 1 plus 2x. No, 1. It will be 1, right?
Okay, so this is 1 plus 2 times 0 raised to the 1 over this sign at 0, right?
Yeah.
Which is this, which is not very helpful. um,
That doesn't give
Approach-
anything.
it does not. If I'm approaching this from the right, then this would become
0.9.
positive infinity, which would go to 1. So
Yeah.
I'm going to check both my one-sided limits for this one then. So checking my one-sided limits, I'll change colors to green. If I take the limit as x approaches 0 from the left, then this will become 1 raised to the 1 over negative infinity. Which is still 1. If we do the same thing and take the limit as x approaches 0 from the right, can't grab that corner. This will become 1 raised to the infinity power, which is also 1. So because my limit from the left is equal to my limit from the right, my general limit must also be the same.
So B. I see.
Okay, and then I've got one more. We've got a continuous function on our interval 0 to 1. We know g at 0 is 1 and g at 1 is 0. So I'm going to draw that really quick. We've got g at 0. So when x is 0, g is 1. So I'm going to say that's right here. And g at 1 is 0. So something like this. I want to know which of these is not necessarily true. The first one says there is some number h such that g of h is greater than g of x for all x in 0 to 1. Another way of saying this is that there is a maximum on this interval.
Oh.
Is that true or not true?
Yes.
Okay, this one is true by the extreme value theorem because we are continuous. For all a and b on our interval, if a is equal to b, then the y values are the same. Is that true or not true?
If A is equal to B, the Y value is the same. No.
So what this really says is if a equals b, so if the x value is the same, then
Okay.
GA equals GB, then the y value is the same. So at the same x value, do we have the same y value?
Yes.
Yes. By definition, a function is an equation that has only one y value for every x value. So this one is also true.
Okay.
There exists a number h such that the y value is 1/2 between x equals 0 and x equals 1. Let me draw the y values on here. This was y equals 1. This was y equals 0. This was x equals 1. Okay, is this true or false?
It can be true because it's in 1/2.
Can be true. Does it have to be true though? So it says there must be a y value of 1/2 for some number between x equals 0 and x equals 1.
It doesn't have to be true, but
Because this one actually does have to be true because our function is continuous. There is no way to draw a line
okay.
between the first point and the second point without passing through 1/2 at least once,
Okay.
if we are continuous.
Then the D is not correct because 3/2 is 1.5 and it's beyond the 1.1.
Perfect. D is not true. It is possible to draw a line between these two without hitting 3 halves like this.
Okay,
As a
yeah.
counterexample. So the intermediate value theorem guarantees we will touch every y value between them as long as we are continuous, but we don't have to touch a y value that's not between them. Okay, and the last one, for all h, our general limit is equal to the point itself. And that's my definition of continuity. And because we are told we are continuous, that must be true as well.
Okay, it has to be an open interval. Oh, gx equals gh. Okay.
So the reason why they rewrote their interval notation like this is because in interval notation, your parentheses means not included. We don't know anything about the limit as we approach 0 from the left or the limit as we approach 1 from the right, which is the reason why they cut off those points. In interval notation, these matrices, so square brackets, means included.
Okay, thank you. Can I check if question 78 is A?
Hold on. 78.
The last one.
Last one.
Fx is it should be the -1, right? No. Yeah.
Is f prime e where f of x is natural log x. Okay, that's correct.
Oh, so it's A.
Yes.
Okay. Okay, thank you.
No problem. All right, I'm gonna go ahead and cut off here, I think, and hope the recording worked. Thank you so much for coming.
Thank you for teaching.
Bye.